So on the bench today we have another Nixie instrument, the 5245L, which is a frequency meter from HP, of course, and it's an oldie but goodie, so it's in one of the oldest catalog I have. There it is, new and available in mid 1963. Hello and welcome back. If you follow the channel, you know that we already repaired a Nixie counter, the HP 5327B, which to our surprise worked all the way past 500 MHz. We even adapted it to display the mission time from our Apollo Central timing equipment. But the 5327 is modern electronic switchcraft. Being from 1971, it has integrated circuits all over it and would have only been available at the very tail end of the Apollo program. What we have here is much older, from 1963, and you won't find a single integrated circuit in it. This is all made with transistors, and its digital memory is courtesy of neon lamps. So you'd think it would be anemic compared to its 1971 brethren. But you would be so wrong. The base unit goes to 50 MHz, but it has a drawer to the right, where you can put high frequency plugins. At release, a plugin for 500 MHz was available. In 1964, a plugin for 3 GHz was added, followed by a 12.4 GHz plugin in 1966. By 1968, a year before the moon landing, it got an 18 GHz plugin. Yes, you are looking at the king of the HP frequency meters in the 1960s, and you bet that this one was used in the Apollo program. You can see a whole row of them in this picture from the Apollo Space Communication Ground Station in Honeysuckle. While we are at it, you can spot two other digital HP instruments in the racks. They are a bunch of Dimec DY2401C 6-digit digital voltmeters, and a couple of HP 5100 digital frequency synthesizers, also from 1963. It might be the early 1960s alright, but the finest instrumentation is already squarely in the digital age. We will still give an appreciative nod to the HP 413 AR null voltmeter, a renowned vacuum tube voltmeter. Also special mention for the Tech RM503 scope atop the stack. While we are at the top, we spot an HP 394A variable directional attenuator, good to 2 GHz, no doubt connected to the amp for the big antenna. Anyhow, a microwave capable Nixie frequency meter that was used in the Apollo program. Oh boy, we can't wait to save it. But this freebie donation is a known toughie with prior unsuccessful repair attempts. In fact, I don't think I had ever seen an HP instrument with so many faults in it. Plus I have acquired a whole bunch of broken plugins for it. So repair-a-thon it will be. So the frequency meters were one of the first instruments to go digital. And this is the second or third generation of it already. And this one doesn't work, it doesn't count. The converter here is stuck. This one goes to 500 MHz. I have the whole series. And this one goes through 12.4 GHz. So it's a really potent counter. Yeah, this we cannot probably pull out without putting something, but they are the dividers. So this is a... each is a divider by 10 and counts in BCD, then the neon and photoresistor, BCD to Nixie driver, and then the Nixie driver. The neon providing memory, by the way. And it's the very early oven oscillators, and a whole bunch of things for timing. Transistors. And here we have Antoine.
Hello.
Yeah, actually, you want to turn it on, see what happens?
Yeah.
I've done that before, and the Nixie did light up, I think.
How did you? Is there a switch in the back?
No, I think it's here.
Over there.
So let's get this one in.
Oh, that's how you.
Oh! It has.
There's some light.
It has Nixies.
There is some light.
It has Nixies. It's zeroed, but it must be a test check.
It doesn't do anything.
Start, stop. When the thing can do period average and ratios of frequencies. It's just remarkable. So I have now 1 kilohertz over here and frequency megahertz, kilohertz, and we get nothing. It's 2.5 volts, so check, level plus, minus, so 1 volt should be fine here. Yeah, okay, so that's what I remember. It's not even starting. Come on, start. We should have a gate and it should count. You should count. And it don't count. Okay. Just quickly checking power supply. The minus 15 is 5, minus 15.001. 13 volts, 13.029, and there's like 1.6 millivolts of ripple. So all power supply is adjusted to 2 decimals. That's not a coincidence. Someone was in there recently and adjusted them to perfection. It's not a simple power supply thing, so let's check the crystal oscillator first. So we've hooked ourselves up to the back of it. We should get the 1 megahertz frequency. Oh yeah, actually not. There you go, there it came. Alright. 1 megahertz. We got it. Very nice, the crystal oscillator works. And very conveniently at the back of the instrument, a switch allows you to get all the divide by 10 reference frequencies plus 1 multiplied by 10. So we can check all the divide by 10 and the by 10 multiplier. That's 10 meg. Here it is. 100 kilohertz. That works. Okay, so that's, we have happy dividers here. That's pretty cool. You have a time-based reference at the back from the oscillator, so it should be super precise. Okay. So that works. So our crystal oscillator is crystal oscillating. So that's very good. Seems to be working fine. And the 10 megahertz is multiplied. That works. Let's look at the front. So if I read the schematics properly, this should also give me gate signals. So we got something. 10 milliseconds. Yeah, timing looks okay. 1 millisecond, that's correct. 0.1 millisecond. That's correct. It gets smaller and smaller. Ooh. It doesn't look like it's making the whole... Huh. So that might not be normal. Oh, it's because there is nothing coming at the 0.1 microsecond. It's there, but very little of it and deformed, okay? So our multiplier might not be working. Okay, we seem to have our first problem, the 10 megahertz multiplier not working correctly. We'll look at it shortly, but before we got there, we elected to clean all the edge connectors, just in case, and take a look-see at the underbelly of the machine. So we took the back off, and we got greeted by this beauty. So a hand solder backplane with a few components in between. That must be the input. Whoa! Input amplifier, that's not, kind of floating, the connector is floating. A board here which is missing a fastener. Okay, this has been monkeyed with. And so Antoine, this board has no fastener. So
oh, it has not. It has been
so
opened.
So somebody has wanted
Yeah.
it. This one is not attached either correctly. So there's been some monkeying here. And I suppose this is the input amplifier. The interesting board here. Distribution most probably of the signals, or gates, selector gate, for which of the divider you use. My suspicion is that there has been an attempted repair here. That's correct. An intermediate board, a beautiful hand solder backplane, and then bits and pieces of power supply all wedged in there. That's going to be annoying as hell. Alright. Oh, there's even a board down here. Look at that. Wow, so there's stuff everywhere. So as expected, Deoxit didn't do a thing. We're still not counting, and we're missing. We have hardly 1 megahertz and 0 times 10. So something's off in our multiplier, I would think. Alright, so from the schematics it tells me that I should have 10 megahertz created by this and come straight out of it, and I'm measuring something very, very weak. So I don't think it's my only problem, because I'm still not counting, but that's the one that's used for checks, self-check, so that's not gonna work. So I have instrumented my multiplier here, so I should have times 1, times 2, times 5. So 1 megahertz, 2 megahertz, 10 megahertz, and then the output amplified. And it takes a while for it to come on. And we have the 1 megahertz, really strong. For the times 5 look like it's not tuned properly. Looks like I did. So although I have my 10 megahertz back at full juice here, on the output here of the gate, I still get the lower speeds okay, but the 1 megahertz and the 10 megahertz, they are no good. So we have a problem somewhere, and even if I do that, that's just the gate, so that's not going to affect the counting, so I have other faults in there. Okay, so back to trying to get my 10 megahertz signal that doesn't come out. Now it comes out of here. We saw it out of here, the multiplier assembly, and it doesn't come out of here all the way at the end, which is my switch. And you go where it goes, it simply goes through that gate number C, which is on A35. So let's go to assembly 35, which is conveniently open here, of course. So 10 megahertz comes in here and goes in here, and that's the famous gate right here. So let's check what comes in here and if I can get it out of there. And board 35 is at the back of the machine. And here's our Q2 with 10 megahertz in, and should get 10 megahertz out. And in is in green and out is in yellow. And I think we have spotted a problem. Here's our 10 megahertz, which is now okay, over a volt peak to peak. And out, it's an emitter follower, so it should be over a volt peak to peak, and it's nothing. So either bad transistor or something bad further down the chain right here. Right, Q10 is out. It has this little ferrite bead on the emitter. I found it. It was on there too. Let's test if it's good. Alright, on my right, 2N2222, a switching transistor, 40 volts, about 400 megahertz, low VSAT, beautiful transistor. On my left, from the HP instrument, a Twin708, a switching transistor, low VSAT, 40 volts. Ooh, not a transistor anymore. So I think we have found our first bad part, and we're going to replace it with a 2N2222. Unfortunately, I don't have a metal can version of it, but this one will have to do. Okay, our new transistor is in, unfortunately not a metal can one. And let's see if we can see some improvement. in green, out in yellow. Takes a while. There we go. We got 10 megahertz out. Much better. Okay, so my 10 megahertz is back, but not too surprisingly, I am still not counting anything, and I thought that would happen because the 10 megahertz only involved in the higher registers. So I decided to follow the signal from the input amplifier, which was the card that we saw had some work, or at least was loose, and make sure we don't have a problem with the two FETs and any of the transistors here. So the amplifier is this loose card over here, and the output is clearly marked. And see if my FET is blown, and it is not. There it is, beautiful signal, and no, can make it bigger, smaller, so the input works. Also the this guy used not to work, but that was mechanical, so we can center it. So input amplifier, perfect. So this is good because I don't have to track down some FETs. So my signal makes it from its input to the output, no problem here. And it tells me it goes to the next page, which is this one, which is the other card that was loose. And this is a little bit more complicated. What you see here are diode switches. So it's a whole bunch of things that select what gets measured. And what's of interest to us is the input signal comes from the other card, and this diode switch, and then it goes over here. So I've hooked myself up to the first emitter follower, so I should get the same signal I get at the input, but then I should be able to select it and see if my diode switch is working. On the instrument it's that card, and it's, I think I'm hooked up on the green wire here. So that should be the green signal. Bring that down. And the green signal is there, it's perfect. It's an emitter follower, so it follows the input. But now, can I select it actually? Interesting. So, yeah, that's still a frequency measurement. If I go in period, okay, so it has switched to another input, and I suppose this is the period time. Okay, this works fine. So great, my input switch works, and the input gets to the first stage. Alright, so then I was following it. So there's a series of amplifier, and the next point is, I think I am on Q4, and that should be the same thing but amplified. And that's my blue probe. Well, not only it's amplified, but it's now a square wave, right? So that's ready for counting. It's been amplified so much that it's a digital signal. Very, very good so far. Next probe I have, which is a red probe, is on this stage here, and I am on the collector at 0.17, which is the entrance to the gate. So if the signal makes it to the gate, then it's a problem with the gating or the counter. We don't know yet. That's also one of the probes. That's the red probe. I'm on the collector of that transistor back there. And that's the red button. And here, surprise! We get nothing. It's a perfectly good signal at the input, and now 0, zippo, nothing at the output. So that's another 2N709, 708. So let's check that transistor. Okay, what the heck has happened to this guy? These two transistors, Q3 and Q4, should be the same. And obviously they are not. They're completely different models. They are all soldered sideways on long legs. This whole section has been messed with. None of the transistors are straight. And yes, they all have been changed. So I better... I'll check my Q9. Is this fellow, which, oh, interestingly, it's one of the few that hasn't been changed. So they changed everything but not Q9. And I better check and put the correct transistors here because I bet you they are not. Alright. So I couldn't find what Q3 and Q4 were. They are 1854073 and they have no known cross equivalent, which means that usually they don't have a JDEC number. And I found it in my HP Fish. So it's a low noise figure, 4.5 dB noise figure, low current 2 milliamp, no average gain 150, but 750 megahertz. So it's a high performance low noise RF transistor. And do they have something that's close? They do, somewhat equivalent to a 2N3478, which is the same except it's better. It has lower capacitance. So yes, that's what I should replace it with, 2N3478. So looking at what they did down here, this transistor is the correct model. So they replaced it and they replaced it with the right one. This one is very wrong. This should be a low noise RF transistor, 750 megahertz, and replaced it with a 2N709, which is a lower frequency switching transistor. So definitely not the correct transistor. The one that looked weird is actually the original. So that's a race transistor. It's the famous 0073 with an HP marking. And all these are correct, either replaced or original. And this is the 709 that I think is dead. So maybe I switched that 709 over here and I put the correct RF transistor. The correct one would be 2N3478 or one of my two other vintage race transistors that I have here. This one with which I've repaired the other counter, or even one with 1.6 gigahertz, which is even lower noise figure, 3.5 dB, but has 4 leads, and it's always dangerous to put one that's too fast. It could oscillate, although I think that circuit is used at fairly low gain, but I'd probably replace it with that one, which is 800 megahertz, and a little bit higher gain, so that should work. But first thing first, before I replace the wrong transistor with the right one, is that do I actually have a dead 709? We are going to find it pretty soon. And the 709, once again, you can replace them with 2N222, so those are easy to find. So 2N709, is it good? Is it bad? It's good. Ooh. Okay, so that looks like it's a transistor that has too low breakdown voltage. So maybe that's the problem. Okay, I've put the other 709 that shouldn't have been there in the first place. So that's the one we're just testing. Well, it's similar. This one has even lower gain. Well, maybe that's what this transistor is. I'm a little worried that the transistor was not the fault. Oh yeah, 2N709, that's an early NPN epitaxial transistor. It's a 6 volt breakdown voltage. So okay, both of them are good, and I think the gain can be very low, 30 to 90. So both of those transistors are okay, so my fault is somewhere else. So I forgot how poor the early epitaxial NPN transistors were. So these are 709, which is within spec. No, it's supposed to be right here, 6 volts, so it does it. And this is a 2N2222 with 3 times the gain. No problem with the voltage whatsoever. So actually, yes, it's a PN2222, so that's an even better one, much better than the original 2N2222. So I replaced my transistor that wasn't correct with one that should be able to do the job, And I replace my 709 where it was. I haven't changed it to modern one, just because it should work okay. So I put my board back and saw the same thing because I hadn't changed the transistor. But now I think I understand why. I didn't realize, but that capacitor here is 10 picofarad. So this is a differentiator. I should just see a very small pulse here. So if I go back here on the trace, and then if I look really good, there it is. That's the differentiating pulse that I get out of this. So it's working. I have a over a volt of a pulse, so it just gives you strong impulsions at every transition. So I think that circuit works. So let's go for it. Alright, so continuing the debug, I'm trying to see if I'm getting a gate signal, and that's the orange wire here, which is actually connected to the yellow line over here. And I see absolutely nothing. No gate. And I should see a relatively big signal, several volts. When I do manually start it, I see something. So I don't have a gate signal, which is a problem. And also when I start it manually, I still don't count. So I have more than 1 volt still in here with the gate and the count. Well, all in all, I'd say we made some good progress on our king of Nixie counters. This really feels like debugging a giant integrated circuit, but with access to every transistor, which is quite satisfying. We got our 10 MHz multiplier back on track, our distribution board to distribute it, and swapped some wrongly replaced transistors with the right ones. We also checked that many subsystems do work fine. The power supply, the oven quartz oscillator, the by 10 dividers, the diode switches, the input amplifiers, all are good. In fact, we get pulses almost ready for counting, although they still have to go through the gate. But we are apparently missing the critical gate signal. So there are more faults in this unit, quite a few actually. But this episode is getting a little long in the tooth, so we'll discover and fix them together in the next episode. See you then!